Good morning, all. This is M. Paramesh, convener of 5-day online faculty development program on recent advances in electrical engineering. Welcome all of you for day 4 session. On behalf of Department of Electrical and Electronics Engineering, Gates Institute of Technology, I thank each and everyone for your active participation for day 3 session. I hope you all had an interesting and knowledgeable session on day 3 on impedance source inverter for renewable energy systems by Dr. Manoranjan Sahu sir. And I hope all of us get new ideas by the end of this 5-day faculty development program. Now it's time to start our today's session. Now I would like to invite Mr. Lakshman sir to introduce today's speaker.
Thank you, sir. Good morning, one and all. I am M. Lakshminath, Assistant Professor, Department of EEE. It's my privilege to take the opportunity to invite today's resource person, an eminent speaker, Dr. Damodar Sivakrishna Rao Kasagani, Assistant Professor, NIT Srinagar. Sir did his BTech from Kakatiya University in the year 2010, and Sir did his MTech from National Institute of Technology, Tiruchirappalli. And also Sir did his PhD from National Institute of Technology, Tiruchirappalli on solar photovoltaics. Sir has teaching experience in prestigious Indian institutions. So he worked as a teaching faculty in National Institute of Technology, Tiruchirappalli. He served as an assistant professor in the Department of Electrical and Electronics Engineering, Birla Institute of Technology, Mesra. He worked as an assistant professor in the School of Electrical Engineering, Vellore Institute of Technology, Vellore. He had worked for the establishment of NABL accredited calibration laboratory in the NIT Tiruchirappalli. He had an experience in the field of calibration of as a technical manager. So his research expertise includes solar photovoltaic systems, which includes grid connected and standalone forecasting techniques and MPPT techniques. He is currently working in the area of electric vehicles and smart grid technologies. He has guided the UZ and PG students in the area of distributed energy generation. He had collaborated with various industries to perform energy auditing studies. I would like to invite Dr. Damodar V. Sivakrishna Rao sir to take over the session and enlighten us with his experience. Thank you, sir.
Sir.
Sir, good morning, everyone, sir. Am I audible, sir?
Yes, sir.
Sir, I'm very good morning, and I'm very thankful to the speaker who introduced me, and I'm thankful to head of the department for inviting me for giving this guest lecture, and management of Gates Institute of Technology for today's session. And I'll start my presentation in a couple of seconds. Yes, sir. So I hope my screen is visible to everyone right now, sir.
No, sir. Hi.
Sir.
Visible, sir.
Yes, sir. Okay, sir. Yes, my presentation, the session will be starting on like role of forecasting in renewable power generation. So my presentation, the next 2 hours will be having two things. First one is the general description about role of forecasting in renewable power generation, the state of literature, what's happening throughout the India and throughout the world. Like what forecasting has plays a role. Generally, the forecasting is meant for some managemental people, but for coming to our electrical terminology or engineering students or engineering researchers, how it will be seen that forecasting will be needed for us, mainly for renewable power generation and electrical engineering point of view. And the second thing, I'll try to address some research problems or some case studies, what we can do, the implementation of forecasting techniques are in our electrical, maybe renewable energy power generation can be a wind or can be a solar. So myself, DV Sivakrishna Rao, I am working as current assistant professor. I am welcoming everyone for the today's session. So contents of my presentation, first of all, why the forecast is needed. And again, there are so many techniques in forecasting, but we'll see some techniques which are useful to understand the data pattern and what are the different models in the forecasting and forecasting methods. And we'll see different case studies, research point of view, that how we can implement these techniques to our to address our research gaps, or to find out some useful, or to generate some useful information from the given data. So coming to the introduction, so what is forecasting? So first I'll go with a brief introduction about forecasting. Coming to the power system planning, I'll directly go to the power system planning, resources planning. So the power system planning will be mainly can be done by forecasting only. For example, we need to forecast what is the maybe the 1 month, because here we have different time horizon, because the forecasting, the major point is time horizon. So time horizon in the sense, in future, at what point of it's called point. So for example, are you want to forecast 1 hour ahead, or 1 day ahead, or 1 month ahead, or 1 year ahead? So this 1 hour ahead, or 1 day ahead, or 1 year ahead, it is called time horizon. So time horizon decides our area of application. For example, if you are doing for load scheduling, so load scheduling maybe will be, we have to go for 1 hour ahead and 1 day ahead. For example, if you know if the power demand, if it is, if I say 1 day ahead, so if you know the power demand for tomorrow in the given time slots, so you can plan your resources accordingly, like what is the power, what is the amount of power you can generate from the generating station, or it is called generator scheduling, how you can schedule it if you know the forecasting value or the future value of the power demand. Similarly, if you want to expand for the power system expansion, or you want to go for a new power plant establishment or a new unit establishment, so we have to forecast I can say the next year what probably the what is the value of the power demand, or the load demand. So if you forecast the next 1 year, next 2 years, what is the power demand? So based on that, you can plan your resources or installation of the resources accordingly. So this is where the application lies, the forecasting in our power system applications. And maybe the power system planners and the energy traders, for example, nowadays renewable energy, maybe the wind and the solar, or the plants, whatever we are installing everywhere, we are injecting the power to the grid. So these resources, whatever they are generating, for example, solar power generation is unpredictable in the sense, we have to see that the demand, whatever the generation, whatever we are doing, it is not uniform. It is depends upon the so many other parameters. So even to integrate our solar power to the grid, or wind power to the grid, first of all, we need to forecast the solar power. So how much power you can able to generate for the next 1 hour, or for the next 1 hour, or next 2 hours. So renewable energy generation, mainly forecasting plays major role. So that's why the forecasting, whatever the managemental people till now they are using for their sales production, sorry, sales estimation and sales forecasting, and they want to do the economical, like economical forecasting, like what can be the GDP, or what can be the next quarter results or performance or the profits. So generally these applications we will mainly find out in managemental point of view, but we'll try to apply how these techniques will be useful to our normal engineering problems, to address our engineering problems. So it is very basic definition. It is nothing but predicting a future event, nothing but a forecasting. So what is the underlying? Generally, this is for business decisions for electricity markets. So we have broadly classified forecasting approaches into two types. That is what I'll briefly tell: qualitative methods and quantitative methods. In our engineering application, qualitative methods may not play a major role. Will the next coming slides, whatever I'll present on quantitative methods. So what is qualitative methods and quantitative methods? So if you see nowadays, everyone is talking about data mining and big data. So everywhere we have so much of data is available. We have to get some inference out of the data, or you have to process the data. So this data processing, like quantitative method, it's needed some data to process it, and from the data we will try to forecast the future value or the output value, whatever you decide for, what you are looking for. So but qualitative methods, it is like we need some experience, some expertise in the area. So the qualitative method will not need any data needed for it. It's need only the a group of people who are having experiences in different fields, so they can able to tell what can be the value. For example, it can be we want to see some in the marketing, we have so many models are there. So like what model can be in future, it can come. For example, we have done some 4 or 5 models in the vehicles or the manufacturing. So what model can be implemented, or what model still you can able to release the market, that will depends upon the expertise or the experience of the industry people. So there we don't have any data. But coming to the quantitative method application, like for example, how many units of a particular model has been sold or can be sell in the next quarter, so that can be given by quantitative method. So our engineering application mainly talk about quantitative methods, because we have all the data, or we will try to get the data. For example, the load demand, we will have the past load demand. For example, if you talk about 2018, 19, 20, what is the load pattern? Based on that load pattern, we can predict the future value, or we can forecast the future value. So all our majority of the applications, I can say it is come under quantitative methods. So whatever I explained now, these are all slides I'm showing it. So you see, it's qualitative method, it's involved experience, and coming to the quantitative method, it's need some data, historical data. And by default, I said quantitative methods involved so many mathematical techniques. And nowadays, the forecasting we are doing with artificial intelligence techniques and machine learning techniques. So in that, I'll try to see that maybe the ANN artificial neural network, how the artificial neural networks will be useful, or will be useful our application for doing forecasting. So coming to the quantitative forecasting. So we have quantitative forecasting, we have so many forecasting methods. I'll try to discuss that. So we have to forecast the value, and we have to evaluate the forecast. For example, there are some stages in forecasting. I will show in the next slide. So coming to the quantitative forecasting methods. So what are the basic quantitative forecasting methods? So first of all, I already told you that we have certain data pattern. So that the data, based on the data, we have to see that what is our application. So quantitative forecasting, we have a time series forecasting and the time series models and the causal models. So coming to the time series models, that means there is a sequence, like for example, day 1, day 2, day 3, day 4, day 5, and what will be the power output and day 6. For example, we have solar power generation. We are generating started from day 1, and we have data up to day 5. So we want to see that what is the power output at day 6. So these are all time series. Like we have a time interval of certain time interval between the data. Then we will try to extrapolate the value, and we are trying to forecast the 6th day output. But coming to the causal models will have some relationship. For example, I want to predict solar power output, I want to forecast. But if I model it as a time series model, it may fail, or it may have some more I can say accuracy problems. But this solar power output will depends upon the solar radiation. That means if you know the solar radiation value, you can able to predict or forecast the solar power output. So this is by default. In this case, solar radiation data is called explanatory value. Explanatory variable means we are forecasting the output with the help of an explanatory variable, or with the help of a variable which will have effect on the output. So for example, if you want to forecast maybe the wind power output, so there are so many factors which will influence the wind power output. So that maybe the wind direction is the one parameter, maybe the geographical location will be the one parameter. So these are all called influencing parameters. So in our literature terminology, we will name it as explanatory variable. So this explanatory variable, if you use to model that, they come under causal models. So the time series models, the moving average and exponential smoothing and the trend models, I will explain briefly that maybe this will be useful those who are about to start their research in the forecasting, what can be done once you have certain data, or once you have certain application where you want to implement your research findings. So generally we have to see the data pattern that I will explain that. In the causal models, we have regression. Regression analysis can be done. It's simple mathematical technique. But other than that, the same regression model, sorry, we can implement by using machine learning techniques also. Yes, these are the research basic steps. Those who want to do the research in the forecasting may be useful to our maybe the smart grid applications also. Nowadays, the people are looking for 5 minutes ahead and 10 minutes ahead. Like it's a very low time resolution. 5 minutes in the sense, like in the electricity markets, every 5 minutes the things will be dynamic. So we need to forecast what is the solar power, like energy traders. We need to know what is the power generated from the renewable energy, and then the surplus, the deficit of the amount of power we have to plan from our conventional electricity board, right? So what are the basic steps in forecasting? First we have to see the problem definition. So the problem definition is nothing but, again I'm saying, it is the application. Then if you know the problem definition, then gathering the information. So gathering the information, so your problem definition can be maybe you are trying to integrate a solar PV system to the grid. So in this solar PV system to the grid, your problem definition can be next 1 year, if you are installing 1 megawatt power plant, next 1 year, for every day I'm talking about. So how much power you are able to produce, maybe if you want talk about energy point of view also, because this power and energy I will try to interchangeable, I will try to use it. But I can say that how much energy or the power you can able to generate for the next 1 year, or even it can for the local application, or it can be to the grid. So before installing it, we have to know at least that it is called assessment. Before installing any power plant or any wind farm, we have to know the resources assessment. So once you know the resources assessment, it is called on an average per month or per day or per year, how much energy you are able to generate. So there is a minimum value and there is a maximum value, which will be decided by the geographical location, right? So for example, this can be our problem. So whatever the point I said now, this is called gathering information. So we have to gather all the resources availability for the particular location. Then that information, we have to see the analysis in the sense, if your response or the output depends upon so many parameters. So we need to give some analysis between the explanatory variables and your output. And finally, we have to find out a fitting model, or we have to choose a best model for your thing. But how to choose that best model? There is some method called benchmarking, or some statistical analysis or error analysis. So based on that, you can do your best model. And again, I'm insisting now, whatever the model you are designing, that model may be best for your information. That the same model may not give the best accuracy for the other information. So that's why for every information, we need to have a unique model. If information has been changed, I can say the problem has been changed, then you need to look for some other model which will have different explanatory variables. So sometimes we may not have any explanatory variables. And finally, we need to evaluating the forecasting techniques, means benchmarking the forecasting techniques. So quantitative forecasting methods, just now I shown that. In that I'll try to see how to, because whatever the problem definition and gathering information, and step 1 and step 2 I'll explain maybe the briefly. Then I'll try to go for some case study, because it may be useful to the audience who are really looking for, because these are all very basic things before entering into the research or before entering into some area of the work. So we need some information. After that, pinpointly, if you talk about, or else if you narrow down our discussion, then we'll see, for example, particular problem is there, how to address, or how we address it. Maybe the MTech students or maybe the scholars. So how to address that issue, then I will explain that. But before that, before starting, we have to see that what are the drawbacks in the regular in the regular models. Then only you can try to implement some novelty, or you can try to develop the regular models. Then you can incorporate your changes. Then that model can be best for your particular problem. So what is time series? For example, time series, just now I said we should have some response and some data, but it should have some sequence. For example, here I have some output data. It can be power output of the solar PV system, or it can be the load demand. So that's why to avoid the confusion, I simply taken the output. So the output can be anything, depends upon our problem definition. So if you see here, here I have 1 year time resolution. 1 year time resolution. So every 1 year I have some data. Now, if I want to know what is the power output or what is the load demand, for example, this is 78.7 megawatt, you can say the power demand or the load demand, then what will be the load demand at 2000 year 2000, what will be the output or what can be the value. So it is the forecasted value. So based on that forecasted value, if you know the exact value, then you can find out the error. What is the error you are getting? And time series versus cross-sectional data. What is cross-sectional data? In the sense, there won't be any time series in it. We have some certain data. For example, it is very random in nature. Like we don't have any sequence it is following. So in the time series, in the collection stage itself, we have certain method to, sorry, 1 minute. Sorry for the interruption. Right. In the time series data, if you, again, I am saying the problem definition and gathering information. In the time series data, the gathering information itself will have some certain time intervals. So for example, it may start from seconds to minutes or minutes to days or hours or days. We'll have certain equal spacing between each data point. But the cross-sectional data will randomly collect the data. So there won't be any, I can say equal spacing, or I can say, for example, one value of the power can be taken today. Other data can be after 3 days. Other data can be after 10 days. So in this, there is no spacing, but we have certain data. But using that data also, we can able to get useful information. It is possible. Yes, these are the major points before going to the actual narrowing down the topic. But before that, we have to see that what are the major components in time series components. These are all very preliminary studies we need to do in the research point of view. Otherwise, it's very difficult because, for example, nowadays we are doing so many problems in the smart grid. In the smart grid technology, mainly what we are trying to do. For example, we are getting some information like for example, maybe every 1 second or every 2 seconds or every 5 seconds, we are getting the data. We have so many data loggers. So the data is storing in the data loggers. So from that, maybe in the form of Excel sheet. So the data having like maybe the I can say huge data. So but from the data, what is we should get some inference from it. For example, the data showing some. For example, I'll say. The first point is that data is showing some trend. Trend in the sense maybe if the data is some value of the load or the power, is the load demand is increasing every day or the load demand is increasing or decreasing for certain period of time. So there is called trend. So that we have to find out the trend, whether there is a trend or not. Because based on this analysis only, you can apply your particular technique. Then cyclic. For example, what is cyclic means? Sometimes the power demand is high. Sometimes the power demand is low, but it will follow certain pattern. Certain pattern can be, if you broadly tell, for example, if you say in summer the power demand can be high. If you interpret in that way, then every summer the power demand is high. Then that is called cyclic. Then if the data is cyclic, then you have to divide our models accordingly. Then seasonal, because cyclic and seasonal will have a small difference that I'll explain in the next. And irregular. So how to see that? See the trend component. We have the load demand response, because generally I represented here as a response. Means response can be anything. Depends upon your problem. So now whether it can be overall the uptrend, the power demand is keep on increasing every year or every month or every day or every week. So that is one thing, or else it can be decreasing in trend. So upward trend and downward trend. So if you have a power demand, for example, we have certain data pattern, but if you see the overall slope of the line, it is an upward trend. So then if you want to forecast the next will be somewhere here in this line, it will be somewhere here. For example, these are all some 7, 6 are data points. So what is the 7th data point? Or the 7th year output, it will be somewhere else here. Because there is an increasing, then decrease, then increase, but it is overall trend is increasing. So if you see the cyclical component, how it is doing, repeating, but the cyclical component, it will have up and downs, but the movements are along with the trend, it is, we have up and down. So this repeating trend, I already said, we need to identify what is our inferences, how to conclude, or how to make inferences, that we have to identify that why this repeating ups and downs are coming. And we need to see that at what point of time, or because of what influencing parameters, we are getting these ups and downs. So if you try to address that influencing parameters into your modeling, then you can directly, or you can, I can say, accurately forecast our output. So this is about coming to the seasonal. Just now I said seasonal component is that we have certain seasons. Then that seasons can be, you can divide according to our area of zone or our geometrical location. So based on that, you can able to find out where the peaks will come and where the valleys will come. In the either it can be upward direction or downward direction. So we have regular pattern. So in the cyclic, we have a ups and downs. That ups and downs may not be regular, but they are having some cycle. See here how the ups and downs are there. So in the irregular component, it is very difficult to find out irregular component, because irregular component we cannot able to model also. The reason is that in the data we have certain information. For example, the power demand. So out of the 365 days, there will be a power demand. There is a spike. For example, the spike, the actual average demand can be some 100 megawatt if you assume. But certain day of a year, there will be some 120 megawatt power demand. So this 20 megawatt power demand, it is irregular component. You cannot design your system, or you cannot schedule your system for this extra 20 megawatt power demand, because that is a irregular event. That event might happen because of so many reasons. So that irregular component, which may not be repetitive in nature, that's why general irregular component in the modeling itself, we have to avoid that, because irregular component will lead to you wrong modeling. So see, this is, I just now said, it is due to random variation because of unforeseen events. We cannot tell that what event can be happen in future. So that event suddenly will make the spike or can be valley. So this spike is very short duration, maybe one day in a year, because in the complete data point, whatever I'm saying in the overall data, this is maybe less than 0.01%. So it is even non-repeating in nature. The same event, will it happen in future? We cannot say that. It is almost non-repeating. Right. So now, now I have given a small introduction about the forecasting. So I don't want to really exactly go into the in detail things what you can find out in the textbooks, but these are all needed. It's like preliminary explanation whatever I given, because those who are beginners, maybe in the starting stage of their research, so they want to, if they want to do in this area, maybe to publish their papers or their journals, or want to find some novelty in the work, before proceeding that, they have to know that what can be done and what are the different whatever I said now, that components to be observed in the data what you are collecting, or the forecasting model what you are planning for to implement in the system. These are the basic things we need. But now I'll try to make my analysis or my presentation can be narrowed down to the specific application. But before that, I'll try to instead of generalizing it, I'll try to see that. So now if you have a time series data, first, for example, you collected the data with equal spacing, then you know that it is equal spacing, means equal interval of times you collected the data. Then once you get the data, so we have to see that whether the data having some trend or not. So if there is no trend, there are very basic methods called smoothing methods. You can apply that methods, then you can forecast the thing. If the trend is there, we have to use the trend models, because we have an uptrend or downtrend. Some data will not have any trend. Right. So if what are the smoothing methods? We have moving average and exponential smoothing. And what are the trend models? the trend models are here also we have auto-regressive techniques and linear, maybe the regression techniques or the quadratic techniques. These are all the techniques there we'll use to forecast the trend models. But how to find out the trend or whether it is the trend or not? So now anyhow I'll try to okay, fine. So see this. If you see actual, I have certain power demand. So the power demand, whatever I shown you for a particular period of time, maybe these years, these are the years, equal spacing. Then it's a time series. Then I have some 0 to maybe 8 kilowatt. I taken for small example. So here I don't have any. If you see, there is a graph, but if you see, this is not having any trend, because it should have at least a uptrend or downtrend. It is almost a flat line. It is moving around. So what is moving average? So moving average is called smoothing techniques. For example, if you see, this is the power output, whatever we got it. If you try to apply the moving average graph, your output or your graph is almost smooth. That means the irregular components by default they cancelled out in the averaging. So from this moving averaging, it's very simple things. So what is moving averaging? For example, if I talk about what is the maybe I have 6 data points. So what is the 7th day or 7th year power demand for that particular area or particular house, for example. So now here we have so many average points you can talk. For example, we will say 2 moving average, 3 moving average, 4 moving average. So what is the 2 moving average? For example, if you do past 2 values of it, if you do average of it, then it can be the 7th day output. Or for example, if I do day 3 output, day 1 and day 2 has to, or year 1 and year 2 has to average, that will be year 3 output. Then year 2 and year 3 has to average, that will be year 3 output. So this is very basic, very fundamental moving average, moving technique, where this business and economical point of view, the sales point of view, they will try to implement it. But if our power demand point of view also, we can implement, but we have to see that what is the error value. Because this moving averages techniques, it will only useful to you to compare our actual method to compare it. But generally moving average techniques is a very basic technique to use your time series forecasting. Then I have taken a small example. It is also, there is no trend here. Then I can try to forecast what is the output. Just now I told you that this is the output. This is the moving average output. So if you try to take any 3 values of the average value is the response, as the output, then you have to repeat that value for every 3 data sets. Like, for example, if I want to know this year output, then I have to maybe this 96, 97, 98, these 3 values I have to do average, then that value will be your 1999 output. Right. So then from that I have drawn the graph, then you can forecast. Even exponential smoothing also, it will follow the same techniques. But here, I'll tell you the small drawback here. So what is the drawback? That we are going, for example, moving average 3 means you are trying to do past 3 values as the average value. But for example, if it is moving average 10, that means you are going too much past. So the current technology, the current trend will be different. So what is the exponential smoothing will address that issue. The most recent data will be given more weightage than the old data. That is by default, it's a common understanding that generally, for example, if I want to say in the class, I used to say that, for example, if you want to know what is the today temperature. So for example, if you want to know today temperature, at least if I know the yesterday's temperature, maybe for example, 32 degrees centigrade yesterday. So today I will try to forecast it can be in and around 32, maybe 34 or 30. If I have some date, maybe I'll say t minus 1 to our actual terminology, literature terminology. T means today. So t plus 1 means 1 step ahead, t plus 2 2 steps ahead. So t minus 1 1 step behind, and t minus 2 2 steps behind. So what is this point is that, for example, I want to know what is the temperature at t plus 1. So if I know today t and t plus 1, t minus 1, t minus 2, t minus 3, I will give more weightage to t plus 1 and t minus 1 and t minus 2. The weightage will be in exponentially decaying manner. So the past value, the old value, maybe t minus n will be less weightage. Maybe approximately zero weightage, such that the present values or the latest values will have impact on the future prediction. So this is about exponential smoothing. So as the weights, what is the weights? The weights declined exponentially. The most recent data will get the most weightage. This is a common sense, engineering sense, or the forecasting sense. So here we need to know the smoothing constant. Here we can do so many textbooks. If you see, the smoothing constant has been defined maybe 0.1, 0.2. If you try to increase the smoothing constant, how the data will be forecasting, then you can try to compare it. You can take some smoothing constant 0 to 1, maybe 0.1, then you can forecast. Then take the smoothing constant 0.3, then forecast. You can compare the results. So that is called optimization of your smoothing constant. If you try to go in advance, like artificial neural networks, we have learning rate and we have accelerating factor. So these learning rate and accelerating factors, we have to find out by optimization that for our application, what value of alpha learning rate will be suitable to us. So I'll try to explain that whenever that slides will come. So for example, here we have again the same load data or whatever the response. I'm talking about electrical point of view. So I'm saying load always. So I have that alpha equal to 0.2. Sorry. So I have the alpha equal to 0.2. If alpha equal to 0.2, what will be the equation? See that this is E is your output and Y is your, again, Y also your output. So, but here you can see one is forecast and one is output. So now this W is your weightage. So how it has been done, you can see here, it is very, but this is the basic equation. One is the output and one is the estimated value. So the present estimated value depends upon the past estimated value with the present input. So this weights, how it is, for example, this is 0.2, then 1 minus 0.2, which is 0.8. So here we have given 0.2 weightage, here we have given 80% weightage. So that has to be proceeded. Then how, what is, for example, 1996, the power output is, actual value is 6, but our forecast value is 4. Then 1997 it is 5, but forecast value is 4.4. Like that, I want to know what is the power output at 2000. So I have all the data from 1995 to 1999. The power output at 2000 year, it is 4.8, maybe the megawatt. So we can expect this 4.8 megawatt as the load demand. If I am talking about load point of view, or if I am talking about solar power generation, how much you can able to generate at the year, this year from that particular power plant, it can be 4.8. But anyhow, I want to say that solar power generation, I don't want to make it as a time series model. Again, I'm saying the load demand can be a time series model. That's why the power generation and load demand, we have to understand that, because power generation, the doubt will be like this. For example, power generation, we install a 1 megawatt power plant. So why this 1 megawatt power plant after day 5 or day 6 or day 7, why this output will change as a time series model? For example, what I want to say that the power generation from a renewable energy will not be a time series model. Why it will not be a time series model? Because we have the same power plant. For example, if I have 1 megawatt power plant today, will it possible to generate 1.5 megawatt after 1 year? No. If I have 1 megawatt, will it possible to generate maybe 0.1 megawatt after 1 year? No, it is not possible. Means even though if I collect the data in time series, like equal spacing, I'm not talking here about time series, but equal spacing. But I cannot model this as a time series model because the solar power generation depends upon explanatory variable. So I will model the solar power generation or the renewable power generation, mainly whatever our research today topic, renewable power generation. I will not model it as a time series model, but the load demand by the consumers or the load demand in a particular area, I can define or I can model as a time series model. Even I can model as explanatory model, but there I can model both time series model and explanatory model, because the power demand will have, the power demand will be changing, depends upon so many parameters. Maybe the expansion of the loads, maybe the what I can say that the usage of the power supply, maybe installation of the new loads at the industry ends. So based on this, we have so many additions in the power. power demand. So power demand by default, it may increase, it may decrease depending upon the certain scenarios. So the time series model will have certain meaning there, right? So here that's why I taken the power demand concept. So in the power demand concept, again I will try to extrapolate, or I will try to forecast my day 7. In this case, the 7th value. Then see that how the weightage has been changed. If you try to increase the series, so the weight will keep on decreases. So here how much it is 0.2, then 0.2 into 0.8, it will decrease still. Then 0.2 into 0.8 square, still it will decrease. That means the most recent value will have more weightage. If you go past the value, the weightage will be decreasing. So this is about your, our forecasting techniques, mainly the basic forecasting techniques. So then anyhow, this time series forecasting, I'll stop here because I'll try to go directly to the next model. Even because they're all time series forecasting. So finally, it is auto-regressive. Because before that, what are the models? These are all given for students' point of view. For explanation, I kept these slides, but they're all each model will have its own advantages, and we'll try to keep on increase the model complexity. But they're all time series models only with some thing. So coming to the auto-regressive models, here the auto-regressive models will not will regress, like auto-regressive. The name itself will say that we'll have the same data point, but I'm saying that same data series. I'm saying that. So here if you see, for example, this yi-1 and yi-2 and yi-3. So just now I said like t-1, t-2, t-3 concepts. So we have to see that this auto-regressive, the meaning is that the present output will have a strong relation with the past value. It will have a strong relation. So from this we can find out maybe the correlation coefficient, autocorrelation coefficient. We'll call it as ACF, autocorrelation function. What is autocorrelation function? In the data series, if you want to see what is yi, with the yi with the lagged versions of the same variable, how much it is related, or how much, for example, if you want to talk about 100%, if it is a comparison, in the yi, if you take one lag version like i-1, i-2, so how much the autocorrelation function will say that how much the present value having relation with your strongly related with your past value. So this is auto-regressive, means we have to see that there is a chart. I'll show that. I think it is there. Okay. Yes. This is called autocorrelation function. So autocorrelation function, here I can change that lag version. For example, lag is 1, lag is 2. So that this charts indicates that the present value, how it is relating with your lag 1 or lag 2 data. For example, this low value indicates that here, if you see the low value, it is having very less relation with this lag. Maybe if you take some lag value, for example, this is 1. At this lag 1, we have some low value. I'm saying, for example, maybe if I see this value, maybe at this lag of 2, I may have some high correlation. So this autocorrelation function, maybe the autoregressive thing, we'll see that how our present value will having relation, or how the past series data, what value of lag value having more impact on the present value. If you know that particular lag, for example, lag 2 having, or lag 3 having more impact on the present value, then we will try to model the output with the lag 3, or you will try to forecast the output with the lag 3. So anyhow, these autoregressive models we can implement in Excel thing. All right. Finally, just now we have seen the normal forecasting models, but finally, I briefly explained you some 2-3 techniques like moving average and exponential smoothing and autoregressive techniques. But finally, for the same time series data, I have n number of techniques. I have now our query is that we have a forecasted value because we have 6-day data, time series data. 7th day, what is the forecasted value? Out of the given techniques, what will be the best technique or accurate technique suitable to your maybe your output? So we can do that by using error analysis. So what is error analysis? It's very simple that what is the actual value, because anyhow day 7 you don't know, right? So day 7 we can ignore in the forecasting, but we'll start from day 1 to day 6. We'll try to already, because we have day 1 output is there with us, day 6 output is there with us. So for this given known data, what is the forecasted value for the known data? So if you know that actual value and the forecasted value for the particular day, if you see that error in that particular day, then that is called particular error in that particular day. From that we have to find out mean error. There are so many benchmarking. It can be mean absolute error or mean square error, or it can be root mean square error, like I will say RMSE, root mean square error. So these are the different benchmarking indices. We'll try to use multiple benchmarking indices. So the model which will yield best or the least error or the best accuracy, then that model can be chosen for that particular application. So that is what is that meaning is that the smallest forecast error will be your model which will be suitable for our application. Yes, the simplest model. Anyhow, out of the given models, again, one is the simplest model, the other one is the accurate model. So right. So this is about forecasting guidelines. And finally, one last point I want to tell you that yes, we have errors now. So whether our model is accurate or not, before that, we have to see that sometimes the error also will have some information. Remember that error should be always in random in nature. Means error should not have any relation, or error should not have any trend. For example, if you see the graph, I'll show that graph. For example, see, we have error day 1, day 2, day 3, like that we have errors, but still errors also conveying some meaning. Means they're increasing in nature or they're having some trend. So that means your model is still missing some, it is leaving some information. So your model by default will not yield you any accurate, I can say, output. So that's why in this case, we have to recheck your model. So now this is the undesired pattern. We should not decide this pattern error analysis. If this is the error pattern you are getting, then your model having some issue in the incorporating all the information. Then what is the desired pattern? Your error should be a random in nature with the mean value equal to 0. That means it should randomly distribute there. It should not have any information left out in the error. So sometimes if you see random errors will have some cycle. Here it is decreasing trend. Here it will be having some cycle. See, and here it is having some cycle. So these are all errors. This is random error, but here we are having some information. So this residual analysis we will do after implementing our model. Then still if residual analysis also given you the random errors, then that model you can do for benchmarking. Then that is your model suitable for our application. Right. So this is up to the mainly the role of forecasting in our engineering applications. But I will try to go with some case study. I'll try to. Sir, can I proceed, sir, for case study?
Yes, sir. No issue.
Or else, if you say that I'll have some stoppage point, then because till now whatever I have said, it is a basic need for research implementation. Sorry, research foundation. Then we'll try to see that even while current MTech students and PhD students, they are doing some work on some forecasting by maybe for wind farms and solar farms, solar power plants. So I'll try to take that case study.
Sure,
Then before
sir.
that,
No issue.
okay, sir.
No issue, sir. You can.
Sure, sir. Sure. I'll take that slide, sir. 1 minute, I can give the time to me. Then I'll switch out to the slide. Yes. Okay, sorry for the interruption, and yes. Right. Right. So coming to the case study. So till now, I have explained the normal time series forecasting, which will be as a basic study and the preliminary study for doing any research. Then now I'll narrow down my application to the corresponding topic, that is renewable power generation or forecasting of renewable power generation. So how to forecast renewable power generation? In this case, renewable power generation, again it is a broad area. So instead of renewable power generation, I'll talk about solar power generation. The same analysis will be applicable for maybe the same analysis in the sense, the same way of methodology, whatever the methodology I followed here, from the 6 steps what I explained to implement any model or to develop any model, the same steps we will try to incorporate for any renewable power application or any I can say forecasting application. So here my application is, we have a solar power plant. So from the solar power plant, we need to, or we want to forecast so what is the power output in the given time interval, or in the maybe the one day ahead, or the given time horizon. So now the solar power generation power output, or the solar power output forecasting is my objective. So I want to forecast the solar power output. So this is my problem. So for finding out solar power output, so that we have to see that what are the parameters the solar power output or the solar PV power output will depends. So we see, for that we need some subject, maybe the understanding of solar photovoltaics. So what are the major points to be known to forecast or to predict the solar power output from a solar PV panel? So now we have to see that I have already told you that I can model you as a time series model. Even I can model as a time series model. It is possible. Even if there is a trend, I can identify. If there is a cycles, I can identify. If there is some seasonality in that, I can identify. But before that, there are some variables which can decide the solar power output. So what are the different variables? Now by default, you see the solar power output depends upon, or the power output, PV power output depends upon the radiation availability at a particular location. So the radiation availability we'll try to see in the units of watt per meter square. Means in the meter square, in the sense, in the given area, how many watts of the power you are receiving in the given solar panel. So if you know the radiation data, radiation out in the location, then you can know what is the power output. That is one parameter. But not only radiation, for example, temperature of a location decides the PV panel output. The reason is that, for example, the temperature of the location is 30 degrees centigrade. The PV panel temperature will be some 65 to 70 degrees centigrade at the same 30 degrees centigrade. Means it is almost double the atmospheric temperature, ambient temperature. The PV panel temperature I'm talking about, panel surface temperature. But the panel surface temperature have a negative impact on the voltage availability. So for a 1 degree centigrade in rise in temperature, there is a decrease in solar PV power voltage. So that means the temperature have some impact on the PV power output. So radiation is one parameter, temperature is other parameter. By default, the solar panel tilt angle. That means with how much angle you are facing with respect to horizontal. Because if you have different angles, maybe with respect to the ground, it is called inclination angle. If you change the inclination angle, the radiation received by the panel will be different. Then the solar power output will be changing. So this is the one parameter. But then obviously geographical location means latitude of the location will have impact on the solar power output, and the longitude also will have impact on the solar power output, because the longitude decides your local solar time, because local solar time depends upon the longitude of the location. And similarly, if you see other things, if you want to do some other atmospheric conditions, like someone will see that aerosol index, because solar radiation, again I'll address the points, but aerosol index also they will consider as one explanatory variable. So these are all you can find out in literature. So what are the different parameters which will have an effect on the solar power output? And not only that, maybe the dust deposition on the solar panel. For example, so solar panel have a glass which is a transparent in nature. So the glass has to allow the solar photons into the panel. Then only the photon will be absorbed by the semiconductor. Then electron will be released by the solar PV panel. So if there is a obstacle to reach the solar radiation to the panel, that is due to the dust. So the dust also have the impact on the solar power output. So what I want to conclude here is that this is called problem identification. So before developing the model, as a technical engineer, we have to understand that what are the parameters will have effect on the solar power output. Now, how many parameters will include in our model development? That may, because you have to see that you have to test our accuracy of the model also, because sometimes increasing too many parameters make your model inaccurate, because that contribution of the parameter can be negative or positive, right? So now I'll show you all the 6 steps how to implement, or how we implemented that to forecast the power output. So first of all, the model development, just now I said the problem definition, then directly I'll go to the model development. So model development, it's needed gathering of information, just now I said problem definition, then gathering information. So we have to see gathering information. So how we have done, we have taken a time interval of 5 minutes for every day, like every day in the sense, for example, 24 hours. If you want to collect 5 minutes in the sense, total we have 288 data points in a single day. In a single day, we have 288 data sets. For example, 288 maybe the power output, or maybe the radiation data. We have the 288 data points, overall. So that 288 data points per day. So we have to do for 365 days, or we have to do for 3 years or 5 years. So for example, if you see the case study here, how many days we have taken? 3 years means 365 days. Each date is 288 cells. So we have total 3,15,360 data points. So we collected it. So here in the modeling, we have to use certain data points for model development. But whether that model is accurate or not, we have to test the data with the unknown data. Remember, we have to remember that what are the data used in the model development, generally we should not use for testing. We have to use some unknown data for testing. That means for unknown data, how our model is performing, that is called our accuracy. So total we have 1 lakh data points, 1,05,000 data points are used for validation. So now, and again, these are all important measurement instruments, like how we are gathering information. That is also having certain role. That means, for example, I'm collecting the temperature, so we should know the range of temperature and accuracy and resolution, because these measuring instrument accuracy decides our data. I can say the accuracy of the data what you are collecting. Then if you see the panels and pyranometer, what the data we are getting out of it. So here we mentioned that what are the various instruments or the measuring instruments we are using to collect the data, and what are the resolutions of it, and what type of PV panels we use it to collect the data. Right. So now here we want to predict the solar radiation, because our aim is to forecast the solar power output. So to forecast the solar power output, we have to know first solar radiation for that particular location. So first what we have done, first we find out some model to forecast the radiation itself. To forecast the radiation itself. So if I know the radiation, then I can forecast the solar power output. So now the global solar radiation we have collected for certain surface, and again we have taken, and again this is very important, that how we are collecting the data. It is called quality control. Like the data what you collect, it should have certain quality. In the sense, I'll explain that what is the quality control. That means if I say briefly, we are collecting the data. The data having the first one certain intervals, and the second one in the model development we have to follow a justified approach, because that should have a valid approach, because you should not take randomly any value. And again, the quality control means, if any data, for example, here I want to say, yes, if any data is missing, that you have to address that missing data. For example, you are collecting some data. In that, for example, in a given day, we are missing some 4 or 5 data sets. So how to address that issues? There are so many techniques. They are called interpolation techniques. In between that, if you have certain data is missing, you can use the interpolation technique. Or else, just now I told you moving average techniques. For example, you can take past 3 days data, you can average it, or fast 3 data, not 3 days, 3 points data. You can average it and you can fill that cell. That means there should not be any missing data. If you have missing data, then you have to justify that if you are neglecting that missing data. And some days in the given research area, we observe that there are some full cloudy days. In the full cloudy days, there is no power output. First point, there is no power output, because the radiation is very less. It may be less than 100 watt per meter square. From that, we cannot generate solar power output. So what we done that, because we are modeling the solar power output model, so we excluded that model in the development. So in the maybe in the paper writing or in the journal writing, so we have to mention these things. What are the data we excluded in the thing? So out of the total collected data, so 4.25% of the data was full cloudy days. So here itself we are saying maybe the drawback of the model, you can say that your model may not be suitable for full cloudy days. So here itself we are giving one limitation of the model. If you want to extend, increase our model application to full cloudy days also, we have to increase maybe the cloud cover index. That can be one parameter, the cloud cover index, that you can incorporate in the model development. That then that model may be suitable for our cloudy day conditions. And again, I said benchmarking. So here for benchmarking, what type of things you can use? Mean percentage error and mean absolute percentage error, and maybe the coefficient of determination we'll try to use it. Coefficient of determination we'll try to use it. That is called R square. And again here again, if you see, I don't know that if you see the literature, what type of benchmarking can be done. Here also we have so many review papers available. For example, we have maybe more than 40 to 50 benchmarking indices are there. Out of the given benchmarking indices, what benchmarking indices can be suitable? That is also one research topic that we have seen so many literature on that. But again, I have taken some citations of to strengthen our analysis, like why you have taken mean percentage error or mean absolute percentage error or RRMIC. This one like relative root mean square error, because here if you observe the benchmarking, whatever I have done, we avoided the units like per unit system. We are very much about know about per unit system. That means we want to do our analysis in without units. For example, if I use maybe the error, simple error. It will have some units. For example, radiation will have watt per meter square. Power will have watts or kilowatts. So in this case, if you have error analysis with units, the comparison of the models will be complex. The comparison of the methods, accuracy of the models will be difficult. So in that case, we need to convert into per unit system like percentage error. Then it is easy to compare our model performance. And again, if you see benchmarking, how it can be done. So benchmarking can be done by defining our accuracy. For example, this is one ranges. So for this, you should have some citation, or else you have certain justification that. But these are all the international standards that if you see renewable power generation, they are if it is a model is less than 10%, it is they are defining it is excellent model. And if the performance I'm talking about, if the error lies 10% or 20%, it is good enough. Then if it is this range, because this is only for RRMSE. If you want to see for remaining benchmarking, then you have to see some literature and we have to find out that what is the performance index by seeing the range of RRMSE. Then finally, if the error value is more than 30%, then by your model is poor, that means your model is not suitable for forecasting, then you have to readdress the model. So now, coming to the given application, we want to develop a solar radiation model, like for every location in India. For example, we have taken different locations in India, each having different latitudes. If you observe it here, I followed a trend, that is your latitude is in increasing order, like Trichy, Visakhapatnam, Hyderabad, Mumbai, Bhopal, Allahabad. So it is 10 degrees to 25 degrees. Your latitude is increasing order. If the latitude is increasing order and for the given location, I want to develop a solar radiation model which will be suitable to predict the solar radiation. Because if I know solar radiation, then I can predict the solar power output. That is a case study 2. Because as of now, I will restrict myself to case study 1. That is forecasting solar radiation. Then the case study 2, it is forecasting solar power output. Yes. Now solar radiation prediction with explanatory variable. So what is the explanatory variable I have taken? I have taken sunshine duration. So what is sunshine duration? And again, this is also interesting. Like we have a sunrise time and sunset time. So from the sunrise time to sunset time, we can identify that up to, like for example, in an average, I can tell you that it can be 8 hours to 13 hours depending upon the latitude of the location. So we have a total sunrise to sunset time. We have 8 to 9 hours. This is the time where we can generate solar power output from the system, then you can integrate to the grid. So this 8 hours. This 8 hours may not be full radiation. Sometimes you have 200 watt per meter square, sometimes you have 800 watt per meter square. But if you see PV panel, it is 1000 watt per meter square. It is STC condition, standard test condition. They are designed for 1000 watt per meter square at 25 degrees centigrade. So this is the panel specification. But if you this 8 hours or 9 hours of sunshine duration, if you convert into 1000 watt per meter square equivalent value, it can be maybe some 4 hours or 5 hours effective value if you convert into 1000 watt per meter square. So that's why I've taken sunshine duration as the explanatory variable to predict solar radiation. So now how to define it? We have certain equations here. I'm not going it, but you can take any model. This is called linear model. These are all. Then we have taken different first order model. This is first order model. So here, if you want to know the nomenclature, like this is ABR, like this is simply y equal mx plus c. It is a regression equation. M is our slope, C is our intercept. Like here, A is our slope, B is our intercept, and this is our output, and this is our explanatory variable. I can say this is our dependent variable, radiation value. This is our independent variable, solar radiation. So now what is H? Here in this case, this is our radiation, what you want to forecast. This is our theoretical value. There is a formula to find out this. And similarly, this is sunshine duration theoretical value. There are so many parameters. The S0 will depends. That is latitude of the location. Like we have some 5 to 6 parameters where S0 will depends. Then S is our measured value of the sunshine duration. So how to find out sunshine duration? We have certain device called Kambal sunshine recorder. If you use sunshine recorder, you can find out sunshine duration. So these are all a very brief idea. If you like those who want to do the research, then they'll come to know what is each and every aspect of collecting this data. But here I am giving overview of it. But anyhow, we have to know that this is simply a y equal mx plus c. It's a part of our regression analysis, where I explained in the first slide of our slide that normal causal models. That means forecasting your output with your explanatory variable. That is our main objective. So there we can take any basic equations like second order model, third order model, like the explanatory variable, how it is depends upon our output, how it is depends upon explanatory variable, like linearly it is varying and non-linearly varying with respect to explanatory variable. So we want to see that whether it is exponential relationship or we have any other relationship. To know that, we have taken different case studies. So now it is a simple regression analysis. We can do it in Excel sheet, or you can do it in, if you want, you can do it in MATLAB also. It is possible to do in MATLAB. MATLAB, we have one toolbox called curve fitting toolbox. In the curve fitting toolbox, we'll try to implement that. It is possible to find out all the ABCD parameters directly with the coefficient of correlation. So this correlation, if it is generally 0.9, more than 0.9 is will give you that it is better or perfect correlation. But R square equal to 1 is ideal correlation. Linearly they are correlated, but ideal correlation. We will see here the coefficients what we derived for different models. But here this table may not give you any information about the accuracy of the model. So we need to test the accuracy of the model. So here the performance indices we obtained for different models for different indices. But if you see this RRMSE, almost every model has been given the same error value. So it is in the, according to our table, it is in the category of the good category, because less than 10% is excellent. But it is approximately 10%, so it is almost, it is excellent. So again, here we can use our fuzzy control also, fuzzy logic. Like if you define the overlapping period, this is also one more research topic that if you have different error analysis, then if you define the overlapping area, then you can, the fuzzy will classify your model into best, good or medium. Right. So these are all different models where we got the error values. But if you see interpretation of the mean percentage error, mean absolute, I leave it is only absolute value, but mean percentage error will give you one information that whether the model is overestimating or underestimating. Means underestimating or overestimating means whether you are predicting more than the actual value, or you are predicting or forecasting more than less than the actual value. So the mean percentage error, that is interpretation of MPE. So now these are all observations from the table, like whatever I told you that out of the models, which is the best model, and what is the mean percentage error, how it is varying, and what is the positive mean percentage error, what is the negative mean percentage error. The same thing has been given here. Finally, we have derived a table. Just now I said, for the given seasons, like for I'm talking about explanatory variable, input variable, or the independent variable. I define independent variable as a constant for January month. For example, if you want to forecast radiation in the January month, then you have to take, this is the sunshine duration, average sunshine duration, I can say, maybe the per unit in this case, between 0 to 1, it will be between 0 to 1 per unit value in this case. So the constant value of the sunshine duration is 0.77 compared to our actual expected value, because expected value can be 13 hours. S0 is ideal value, SA is practical value. So practically we have 77% of the theoretical value. So January month you can expect 77% of theoretical value. So based on that, you can find out what is solar radiation in that January month. So now this table will give you the clear idea that what is the radiation value. For example, this corresponding to this, if you substitute that value with that coefficient, you will find out some 600 watt per meter square in the January month, average value I'm talking. So 600 watt per meter square, corresponding to that, what will be your power output? So the power output will be your solar, I'm talking about PV power output. So then February, then March, then April, then up to December, we have given what is the sunshine duration for that particular location. selected locations in India. So this data is given for consider locations in India, average value. Now what we have done, that we have taken different locations. Now in the previous presentation, whatever I told you, that there is a explanatory variable like sunset duration having impact on the radiation. Similarly, it is having impact on the PV power output. It is called problem identification. Just now I told you that. But if I try to improve the model, then I will try to increase number of explanatory variables. But the number of explanatory variables, now you see that the model has been modified. If you see maybe the equation, last equation here, whatever I'm highlighting here, this equation. If you, yes. So if you see this equation, yes, this is the equation. We have only one explanatory variable, that is sunset duration. So the sunset duration is one explanatory variable, but we have certain errors. So we want to modify, or we want to improve the error. So we'll use one more variable, that is pi. So this pi is called latitude of the location. Just now in the previous slide, I told you that latitude of the location I am taken from 10 degrees to 25 degrees or 28 degrees. So it is increasing order. So for every corresponding latitude, if I want to substitute that latitude and duration for every any location, I'll find out what is h. So now we try to implement the model performance, whatever the model we developed here. This is a overall model. It's a published model. So this published model we can implement, or we implemented for these locations. Then we tested the RRMSE. We tested the RRMSE in the last slide. Sorry, the highlighted table, because the Tiruchirappalli, it is now it is improved. Previously it is around more than 11%. We got 10.8 now. Now after this we got some excellent performance with 9.8. But remaining locations, it is fairly good, like 25, 23, 17 and 15, like 20. We'll see the error values, they're all less than 30%. According to our classification, they are good forecasting for the given location. See the location range 10 degrees to 26 degrees north. So this N is nothing but northern hemisphere. Now, then finally, we prepared like what are the different models are available in the literature. Then we can recommend, recommend in the sense based on the performances, we can recommend that what are the models can be suitable for our locations. Then what may not be suitable. Then that models, for example, this is model not recommended for our locations. Then we should not use that, because this table can be useful for the researchers. If they want to implement for particular location in India with different latitudes, they can take this table and they can identify which model can be useful to implement radiation forecasting. But nowadays we have this, maybe if you see the NASA, we have some NASA websites, or we have this PVC softwares. If you go and open the PVC software, there if you enter the latitude and longitude, by there you can find out directly radiation values. For example, if you type latitude is some value, some 13.3 degrees. Then if you type longitude, if you type the day of the month, then directly the PVC softwares will give you what will be the radiation value. But here, as a software, PVC software, how it is giving that for particular location, how it is giving radiation value. Inbuilt, they have a model. That model can be this model, whatever I told. So correspondingly, they have their patented model. They may have their patented model. That patented model or published model, they may use as a background application. Then if you enter, for example, my model or our model, if you use sunshine duration, day length, or longitude, or latitude, you will find out what is h. Then this is our model. Then if you compare with this PV model, then what is the actual two values you can compare. Then you can find out error analysis, whether this model is correct or PV model is correct, or you can do with the real-time applications, you can compare it. So I think those who are familiar with PVC software, those who are doing the consultancy works to design PV system for a given area, so they will try to do the analysis before installing PV system in our area or in our institute, for example. So they will do some preliminary analysis that what is the radiation availability, what is the latitude, what is the longitude, and what is the wind speed in that, how many days of cloudy days we can expect in the given area, for example, for our given location. Then correspondingly, they will suggest that if you want to install these many power plant, this much area of the power plant. So what is the battery backup we needed? For example, these many cloudy days are there in that particular area. Based on that, if you have a backup of the battery, then the battery sizing will be decided. So these are all the design analysis before installing the real system into the actual field. They will do preliminary analysis, then they will see the sizing of the system in the PVC simulation software with the real-time application. Then they will try to implement or install the system into the even it is a grid connector, there is no problem, because grid connector directly will export to the grid. But if it is a standalone system having some battery backup and inverter design, so there we should know all this analysis. Right. So similarly, I will restrict my analysis, whatever I told you till now. So this is with radiation prediction by using some explanatory variables. Now the same thing you can do if the explanatory variable is temperature. So just now I told you that temperature has significant effect after radiation. So I will we can incorporate temperature also as explanatory variable. Then you can see a similar analysis. Just now I told you that whatever may be the application, the methodology, whatever I shown you, it is always almost adaptable for every application, depending upon the problem identification. But the methodology is similar. Now whatever I shown for sunshine duration, the same methodology will be applicable for temperature. Now if it is a temperature, if you see, the same is followed, like the same equations. For example, here the same analysis will be followed, and we identify the same tables. Then we finally see the results, that how the error analysis has been done. Then we can compare that out of the two things, temperature and radiation, which is effectively forecasting. That is also possible. Out of the given parameters, we have to do each parameter contribution. Then out of the given parameters, which parameter is individually forecasting your output better. That is one objective. Other objective can be, we can mix different variables. Why not only temperature? We can take one more parameter. For example, here we have some H equal to some value. Then I'll add one more parameter, some Z. Then I'll add one more parameter, some X. Like that I can add. Then I'll see how it is incorporating. This is called mathematical approach. Now, either temperature or any explanatory variable, how it is affecting radiation, we have done through mathematical approach. But this mathematical approach having its own limitations and applications, limitations and accuracy. So now, these are all whatever you have seen, that solar, I can say the renewable power generation application. So we are trying to implement that. But before that, we have done radiation forecasting. Then maybe in the case study 2, I'll straight away. Yes, just now I explained you that how a forecasting has been done. For example, here, right? How a forecasting has been done, and what are the models or the model development stages. It's called methodology. What is the methodology we have to follow? Like I said, problem definition, gathering information. After gathering information, process the data or process the information, then justify the processed information. After justifying the processed information, then we have to go for the model suitable for our, then you have to know whether there is an explanatory variable, how many variables are there affecting your output. Then you have to identify suitable model to incorporate these variables into your model. Right. Right. Now, sir, can I take the questions now, or I can?
Sir?
Sorry, can I take any queries if you from your side if
Yes,
you receive any queries?
Here some questions
because I have so many case studies, sir, because it is going on, keep on going. So instead of that, because I given one is the theory introduction about the forecasting, and the second one is the application of our theory into a problem solving. So these are all general. I have given you narrow down application, but the methodology is generalized to any application, any given problem. So now, if any problem, sorry, any queries if I receive, then I'll try to answer.
Yes,
Maybe then.
yes, sir. So we have received
Yes,
two
sir.
questions from the participants.
Yes, sir.
So first question, sir, can we implement artificial intelligence in energy forecasting? Sir, once again.
Yes, sir.
Can we implement artificial intelligence in energy forecasting?
Yes, sir. You can implement the next case study will be implementation of artificial intelligence techniques in forecasting, energy forecasting or power forecasting. Means whatever till now we have done. For example, if I open this slide, right, I've taken some. So I developed some equations. For example, this is the equation. Yes, this is the equation we developed it, right? So the same equation we have gone through the mathematical approach. We have gone through the mathematical approach. Instead of mathematical approach, this can be implemented by artificial intelligence techniques. In that, we have taken ANN, artificial neural network technique. So artificial neural networks. So we have different artificial neural network techniques, but I'll explain that. Yes, the question answer to the question is that we can implement artificial intelligence techniques, especially the ANN have large scope in this forecasting, and it may yield better accuracy compared to your mathematical approaches. Yes, sir. Then next question.
Sir, next question, sir. So which development model is better for forecasting of solar?
Yes, sir. I think I will clear this question again. The forecasting technique, I'm saying the forecasting models are not unique. The forecasting models are not unique. Means each problem will have its own accuracy issues, and each forecasting will have its own advantages and disadvantages. But what forecasting technique will be suitable to our application, will be suitable to the given problem depends upon the information available to us. For example, sometimes we don't have any explanatory variable. That means we have only, for example, we have only power demand. We don't have any other data. We have some day 1 to day 30. We have only power demand is available. Like how the power demand is related with our explanatory variable. For example, population size. For example, number of hours of load connected. Like these are explanatory variables. This information is not there with us. So we have only for the power historical power data.
Sir.
So if there is historical power data only is available, then we have to choose techniques accordingly. Sometimes we have explanatory variables available. Just now I said number of loads connected, number of hours the load is switch on or switch off. If you know this data, we will try to forecast your power output with this explanatory variable. So that's why the answer to the question is that the model what we developed is not unique. It is depends upon your problem identification and the data what we collected.
Okay, sir. Thank you, sir.
Yes, sir.
Sir, it's your presentation is completed, sir.
Yes, no, I have one more small presentation on because just now I explained you one case study that is on mathematical approach. One more case study, it is on ANN approach, sir, artificial neural networks. Because those who are very much interested, coming to the research point of view and publication point of view, so people are looking for machine learning applications. So I'll try to whatever till now we have seen for this 1.5 hour or 2 hour session. So I'll try to give you some brief introduction or brief presentation about case study on ANN. The theory behind it, maybe some 2-3 topics I'll try to explain what actually can be done by using ANN. Then I'll leave it to you, sir.
Okay, sir. Go ahead, sir. Thank you, sir.
Okay, sir.
Go ahead.
Thank you. Okay. Now, whatever we have seen that the forecasting models and the case studies with mathematical approach. The mathematical approach is, I can say, maybe the regression analysis we have taken, regression analysis. and that can be a linear and non-linear models. We have taken like a second order model, third order model, and we have taken different scenarios. But the mathematical approach, generally we need to understand each and every step, then we have to find out the output. But coming to the artificial neural networks, so I'll tell you the brief about artificial neural network. So what is ANN? ANN, I'll give you, yes. So now this is simple, very basic layout. Because what is inside, I'll try to explain you, or try to, because this subject itself having n number of applications. The NN artificial neural networks we can use for pattern recognition, we can use for classification, we can use for forecasting. So the application is not unique coming to the NN, but whatever I will explain here, whatever I'm going to explain here, it is specifically for solar renewable power forecasting applications, mainly forecasting applications, especially for renewable power forecasting applications. So what is here that we have different ANN modelings or ANN. First one is ANN having different stages. So first of all, what is ANN? So ANN, generally, if you see any Wikipedia or any literature, they will say that it is like a neuron, like a human brain. What it will do, it will have some memory. For example, we have certain data. So the data will be given to the neuron. So the neuron will learn from the data, like will be from the experience. Then if you give any new data, for example, this is a neuron, whatever I told you, hidden layer. This is neuron number 1 to neuron number 10. So for example, we have a neuron. So neuron has given some data. It is learning from the data. Then it is having some, but how it is learning, that is called, it is called learning functions. So how it is learning will be defined by the learning functions. We have some mathematical functions. Then to learn that neuron, so we should give some training. So what are the different stages a neuron will have, a neural network will have? First, you should train the network or give the information to the neuron. From that information, it will train from that information, or during training, it is called learning. It will learn the information. It will learn the pattern, or it will learn the relationship between the data. So it is called learning. It is called learning. Then after learning, it will try to produce the output. So we have training, learning, and validation. But it will give some output. For example, this will give some output. But how to find out whether the output is correct or not? So it is called validation. So this is called, we have 3 stages: training, testing, and validation. So these are all basic idea about ANN. Then, but how the ANN will learn? There are different, again, there are different techniques. One is supervised, sorry, have some disturbance. Okay. One is supervised learning, and the second one is unsupervised learning, and the third one is reinforcement learning. These are the different learnings what we really see into ANNs, how ANNs will learn. But in our current application, unsupervised learning means we don't have any output. See here, we have some certain output has been given. Already output is there. So input is there, output is there. It has to adjust its weights accordingly to match input and output. For example, y equal to some function of x. So now the y is known to the neuron, x is known to the neuron. The function also we define it. The only thing is that this function will have some weights and biases. These weights and biases, like our y equal to mx plus c in the equation, we have m is your intercept and c is your slope. So how this m and c, we will try to identify. These are all called weights here. In this case, these are all called weights. In the mathematical approach, we will try to do a mathematical analysis. But here, this slope and intercept, it will try to do by weights and biases. This is called supervised learning. Supervised learning means it has the target, it has the input, then it has to adjust the weights accordingly to match input and output. The weight and bias at which it will have minimum error, minimum mean square error. So that is the basic functioning of ANN, means we'll do with supervised learning. So what is unsupervised learning? Unsupervised learning, there is no output. We have only the input. It has to learn from the input. Means, for example, you have different inputs. It will try to group the inputs into different classifications. Maybe it will use some probability density functions. In the given input, which input come under which category, it will try to learn by its own. We have different learning rules for that also, like how we have learning rules for supervised learning. Supervised learning also will have learning rules, and unsupervised learning also we have learning rules. So that itself is a separate area. Like supervised learning, for example, we have minimization of error, mean square error. So how to minimize the error? We have certain technique called gradient descent algorithm. We can go for gradient descent algorithm. So that is one supervised learning technique. Similarly, we have reinforcement learning and unsupervised learning. But coming to our presentation, it is a normal artificial neural network which is having feed forward. Feed forward in the sense, if you see input to hidden layer to output, we are coming in the forward direction. But this is called simple feed forward neural network. Like we are feeding information in the forward direction, and how this information is processed, we need some algorithm that is called back propagation algorithm. So the back propagation algorithm means it will generate the weights in a reverse direction. So again, that is also it needs some flow chart to explain that. But these are all the basic ANN technique. Right. So coming to our application, that we have inputs now. It will make the things easy. That what are our inputs now? For example, I want to forecast radiation. I want to forecast R. R means solar radiation. So what are the various inputs I can take now at a time? I can take temperature as input. Now I can take maybe latitude of the location pi as input. Then I can take sunset duration S, maybe S by S naught as one input. See now all the three inputs I can use as a training data set. Like corresponding input, I have output. So this data will be fed to the ANN. So here we can do, we have ANN toolbox in the MATLAB, or you can do with some basic coding techniques, because to make the training and learning, we have certain coding techniques which are available or which you can model it. So we can find out relation between input to output, whatever I shown in the previous slides, in the temperature or sunset duration, the same relations, I can say that the same relation in the sense, the relation between input and output, we can derive by using the artificial neural networks. Right. Now, just now I told you that how it can be done. For example, I have only temperature as the input. Then I can have it's called one input model. That means I can take only temperature as inputs. Then I can take any two combination of the inputs, because this type of modeling can be done in ANN very easily. That means you can change the different combination of the inputs such that for what value of the combination of the inputs, we are getting better output. So like that, we can increase number of inputs. See, whatever it is only single, then we can go for 2 inputs at a time, 3 inputs at a time, 4 inputs and 5 inputs and 6 inputs. If you see this final model, which is having function of so many, for example, your radiation, if your output is radiation, for example, your radiation is function of all these variables. Now, if you substitute all these variables, for example, radiation equal to some constant into K1 into dt plus K2 into T, K3 into S, or K4 into H0. These are all some parameters. This relation you can derive in ANN. So this is ANN 6, means 6 number of inputs has been taken. Right. Now this is whatever I shown you that, for example, we have find out radiation from here by using 4 inputs. Sorry, 6 inputs. You have taken radiation as the output. Then you got the radiation value. Now what is our objective that? Now this radiation will become input for power output. So what does it mean? For example, I want to forecast here. In this case, sorry, here. For example, this if I take it out. So now if it is P of T power, I have to forecast. Maybe I want to take power output T plus 1. One time ahead, I want to forecast the power. So what will be your corresponding inputs? Corresponding input can be radiation, or it can be solar intensity, sorry, sunshine duration. It can be temperature. So you can increase any number of parameter in the input. Then you can forecast or predict your power output. But each variable of input will have corresponding weights. So these weights, whatever I given is only for one input. Only for one input. If one more input will be there, then the neuron will be 2 here. Because here I have shown only single input. If we have 3 inputs, 4 input, then the network complexity will be like this. Yes. We have, if you see in detail, single input, input number 1, input number 2, input number 3. But if I see only input number 1, this will be the diagram. Right. Now, the same again, whatever I told you that the same analysis, we have to define that what are the inputs, what are the time origin, and what are the type of model we are implementing it, because I am implementing it by using ANN, forecasting model type. So someone has asked me that whether ANN will be a model type to be used for renewable. As ANN in this case study, we have used ANN as a forecasting tool to forecast our power output. So, but again, the same methodology, again, I'm not going in detail because the same methodology is same, but the model will be different. Again, I'm saying methodology, whatever you follow for temperature, in the first case study, sunset duration, the second one, the temperature, and now we are doing for power output forecasting. For every output, we are forecasting the model or the methodology, whatever we followed here, it is same. The only difference is that what are the models we are using or what are the models we are developing. That is the only difference you can identify comparing with your previous models. And again, this methodology is like if you go for some publications, we have to show some novelty in the methodology, because if you try to follow same methodology and then we have this what I can say novelty issues. So you want to make some novelty in the methodology. So there we can implement a different maybe some other artificial intelligence techniques, because some researchers, they're using genetic algorithm in the sense they have different inputs like input 1 to input 10 or they have different weights. How the weights are adjusted by using different techniques, they will adjust by using genetic algorithm. So if you try to incorporate some other artificial intelligence techniques, it will become hybrid model. So these are all where literature is still going on and still research is happening there. The novelty they are presenting in the methodology by varying or by incorporating or by hybriding different models. So that's why here we try to make our own methodology by hybriding different models. So that's why I have taken case 1 in this case as a plain model, case 2 as a hybrid model. So here I think here I named it as hybrid model. Yes, hybrid model. So this is where we can have your novelty. If you try to incorporate some other model, then that will be still maybe accurate for our particular application. And just now I showed you that how it has been designed. Then yes, these are whatever I discussed you without the slides, like how your power output can be forecasted by using the historical power, radiation data, temperature data, and one more parameter for solar power output. How many hours the solar power plant is operated? This is TSPV, means times of hours of operation. The SPV plant is in running condition, like radiation is available. So that is also incorporated as one parameter to find out PT plus 1. Like one day here, T plus 1 is the future instant. This future instant in our case study, we have taken 1 day ahead. Then again, if you see the literature, we have different time origins people are doing. Then they are trying to increase the time origin and they are finding out what are the different variables suitable to find out in the particular time origin. Right. This is about forecasting of solar power output by using a simple mathematical technique or by using an artificial intelligence technique. So this function f can be derived by ANN. So ANN will give you the relation between this output to input by through this function. But anyhow, these details I am not going, because our objectives mainly focus on role of forecasting and renewable power generation. So that's why if it is AI only, then I can narrow down, can go that what are the different ANN architectures and how it can be done. Then if it is narrowed down, we are doing only machine learning techniques, application of machine learning techniques. But here I want to give you that role of forecasting into mainly the renewable power generation. So I hope I have given you maybe enough information, the basic platform information to develop a forecasting model. Then those who want to do some publications or some research or some current technology they want to implement, because nowadays people are doing with some coding techniques, maybe in the Python platform, or we have some open source software like R Studio, and maybe we can still use MATLAB itself to implement our forecasting techniques. And maybe the BTech students and MTech students, they are doing it in data mining, data analytics also, they are doing it. But these all will be useful to you to develop the forecasting models. And okay, sir, thank you. Sir, am I audible?
Sir, you are audible. Sir,
Yes,
here
sir,
one
yes,
more
please.
question, sir,
Yes, please, sir.
from the participants. Sir, the question is, recurrent type ANN is better that feed
Yes, sir.
better than feed forward.
Sir, again,
So recurrent type
I am,
ANN is
yes, sir, again, I'm repeating that, sir. Recurrent type and a feed forward, which is better for the given application. We cannot, if you see any literature, we cannot generalize one model is suitable for, like one model is better than other model, because feed forward have its applications mainly because, again, I'm saying that,
okay.
yes, coming to the, again, if you see that the recurrent type neural network and the feed forward neural network, there are some analysis, the comparison analysis are available. So in some literature, because their problem, recurrent neural network is performing better than feed forward network. In some other literature, for their problem, so other model is performing better. So we cannot say that only one model can be better suitable than the feed forward network, because the recurrent neural network have what I said. We can do like feedbacking the weights whatever you are obtaining. We can feedback to update the initial weights. So that is the only difference we can find out. But we cannot say that only recurrent is accurate. But the only we have a what I can say difference in architecture. Like AN and feed forward will have different architecture, and the recurrent neural network will have different architecture. We are feeding back our weights to the preceding weights such that the weights will be updated. So that is one way of change in the neural network.
Okay, sir. Thank you. We will close the session with the vote of thanks. On
Okay,
behalf of EEE department, I would like to thank our today's eminent speaker, Dr. Damodar Sivakrishna Rao Garu, for accepting our invitation and for giving such a wonderful presentation on role of forecasting in renewable energy power generation and making event meaningful and interesting. Thank you very much, sir. Finally, at the end of this session, I would like to thank all the participants of this FDP for glorious presence. I request all the participants to join tomorrow's session. The session speaker is from Abu Dhabi, UAE. His name is Dr. Umesh DS. Thank you all.
Sir, I'm audible?
Yes, sir. Audible, sir.
Sir, I'm
Both the
very much
session.
thankful to the, Parmeshwar sir is keep on contacting me from past 1 week and 10 days. We are in touch, and thank you for inviting me, and even for the management of Gates Institute of Technology for conducting this presentation and sessions. And I hope the participant will get some benefit out of it. And I am expecting maybe the next sessions also will be useful to the participants, and I'm very much thankful to the management and HOD Gates Institute of Technology. And thank you so much, sir.
Thank you, sir. Thank you. We'll
Thank
end
you,
the
sir.
session.
Thank you, sir. Thank you so much. Sir, I'm leaving, sir. I'm leaving the session. Thank you.